So, today we're going to be finishing up chapter 8. I don't really think it's going to take us all that long. In addition, as a reminder, chapter 8 homework and quiz are due on Tuesday. So, finish things up today. If you want me to be able to fill time to ask questions about anything that you encounter doing the chapter 8 assignments. Excuse me. Definitely finish chapter 8 today, and that'll be the last new material before we start reviewing for our test next week. So, reminder of the schedule. I'll try to. So, this is today. Chapter 8 homework and quiz are due next week on the 3rd. The 3rd is also election day, so we are not going to be having any in-person meetings on that particular day next week. So keep that in mind. I'll make sure it's written in an email. So that's December. November. Okay. So next Tuesday, homework and quiz are due. No in-person meetings. Instead, I will have make sure that everyone has access to information that summarizes everything that will be on the next test. We can have remote meetings, pre-recorded things. Your pick which ones you wish to go to, where we will review everything for the coming test. There also won't be any labs at all next week to facilitate you guys having time to study and take the test. As a reminder, the test will become available to be taken next Thursday. It'll be available Thursday through the next Tuesday. It'll work the same as last time. Email me when you're ready to start. I send you the document. Thursday itself, we'll spend the day doing a review, making sure everyone understands what is and won't be on the test. I will post practice problems like I did for the last test, so if you work those, you can come with questions from that. Thursday will entirely be review, so Tuesday, just not in person. And then we'll start talking about, after we're done with the test, we'll do some miscellaneous additional pieces. We'll do a couple extra tiny chapters before we get into exams. But there's actually only about a month left of class, but a little less than a month at this point. So we're in the home stretch, and Christmas is nearly upon us. So, first of all, how are you guys doing today? I hope you are well. And if things aren't great, I hope they improve dramatically for you. And weekend's almost here too, so I'm apparently just really scatterbrained today. I need to drink more water. So, we're going to finish up chapter 8 today. Before we get started with that, does anyone have any questions about anything at all? If you do, at any time, please cut me off and just go ahead and ask them. And now, I believe yesterday, Tuesday, we left off having talked about all four actually, of the laws of thermodynamics. I believe we ended here. And just summary of all the laws. First law is conservation of energy. Second law says the total entropy level of the entire universe is constantly rising. This law says that, the third law says that the entropy of a single object can decrease as you decrease that object's temperature, but to do so you have to take its thermal energy away and put it someplace else. A related concept is the idea of a heat sink. In most machines, a lot of machines that involve a whole lot of thermal energy being produced tends to try to direct that thermal energy away from the mechanism and into some attached vessel where there's already a lot of thermal energy. And if that thermal energy is already in the hot place, it's not contributing as much entropy into the actual machinery. Computers have heat sinks, cars have heat sinks, the cooling system that takes it away from your engine keeps it from melting itself. That reduces the entropy, at least while it's doing the work, just storing it into a place where it cannot do any harm. Now, related to these concepts, we have a formula that is related to this concept. It's a concept I've already mentioned, and it's just going to be one of the two extra formulas we cover today. First is the idea of thermal efficiency. And every single process has some efficiency measurement. Some measurement to tell you how much of the energy put into the process actually becomes work out of the other end. Now, this formula, I didn't invent any of these units. If I did, they would probably make more sense. The variable for efficiency is an nth. Sorry. What this term normally means in mathematics is, you know how we have first, second, and third? It's just the number with some letters attached to it. This is the same kind of a treatment, you just don't know what the number is. So first, second, third, dot, 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 nth. It's something in that series of ranking numbers in terms of places, but it's an unknown place, and so we call it the nth or unknown value. In this particular formula, it is referring specifically to the efficiency of a process, a reaction, any sort of an action that takes energy to perform. And the efficiency of any process is equal to the output of that process divided by the input of that process. So let's say that, who drove here today? All right, at least two people. So when you are operating a vehicle, maybe I'm going to assume gas-powered vehicle. It takes, you put gas into your car. That gas is the input. Energy is released from the gas, and that energy allows the car to work. So let's say you pour enough gas into your tank that's to store 100 joules worth of energy. That's not a lot, but I'm just keeping the number easy to work with. If you put 100 joules of energy into your car's engine, do you think all of that gas is going to create 100 joules of kinetic energy as the car moves forward? In an ideal world, yes. Ideally, we would like every joule of energy we put into the tank to actually do the thing we want the car to do. But frustratingly, in this tangible physical world, most processes don't do that. So a machine's output, and this does also include the human body, since it's basically just an organic machine in terms of the muscles and skeleton. Every single machine never outputs as much energy as was input into it. In the case specifically of a car, the way that a typical gas combustion engine works is gas vapor is pumped into the engine block and it explodes, which pushes cylinders outwards, and the energy from the cylinders repeatedly coming in and out is what's translated into forward motion via a bunch of other systems. But you're creating an explosion, which by and large tends to be hot. So not all of the energy goes into just expanding the cylinders. A lot of it just becomes heat. And the heat doesn't make your car go forwards. This is one reason why car engines get hot and why you need a coolant system to keep it from overheating. So in a car, if you perform an action that takes 100 joules worth of fuel, you might only actually get 50 joules worth of work. Every single process, every time two objects are touching, some energy is going to get lost to thermal energy. Even in your own body, because you move your own arm, your bones touch in your joint, your muscle fibers have to slide across each other. Everywhere there is friction Friction will take energy away from the process and make it thermal energy, and it's no longer involved in the process in a real way. So the efficiency tells us it's a ratio, a percentage that just tells us how much we get back out. The higher the efficiency is, the better the fuel ratio consumption is. The higher this number is, the nth, it's meant to represent a percentage of how much out compared to how much in. If you had a 100% efficient machine, every joule you put into it would become more out. But if you had a 0% efficient machine, it literally wouldn't do anything, no matter how much energy you put into it. So a rock. And this does represent a percentage. When you actually plug in joules over joules, you should get some fraction, some value between 0 and 1. And since these are supposed to be percentages, this is 0%, this is 100%. So you're going to get some sort of a decimal value out of this, some number between 0 and 1. You multiply it 100 to find the percentage. Every single process has some thermal efficiency, and frankly, most machines have a pretty bad thermal efficiency rating, actually. Again, engines get really hot, which means you're losing a lot of that gas energy just to warm up the engine, which accomplishes nothing. Yes?
What about like hydraulics? Does that put out more into
Okay, they do put out more force. Yes, a hydraulic system can amplify force, but it doesn't do more work than you put energy into it. In terms of force, yes. In terms of energy, no. So, quick sample question. One of the places where we tend to use and lose a lot of thermal energy in various processes is, like what I mentioned with the car engine, combustion, which is the science way of saying fire. So let's examine a specific case where we are burning 1 kilogram of coal. I looked up how much energy 1 kilogram of coal should contain, and at least in terms of the chemical energy stored in its bonds that can be released through combustion, 1 whole kilogram of coal should contain 24 megajoules of energy. Mega is not a prefix we've used in here very much, so as a brief refresher, the standard metric prefixes kilo, hecta, deca, base, deci, centi, milli. These are all spaced 10 apart from one another. Mega lives over here. Mega is actually 1,000 times bigger than kilo. Kilo is 1,000 times bigger than base. Mega is 1,000 times bigger than kilo. We didn't really name the two steps in the middle here. We just kind of skipped straight over. I don't know why we named these and didn't name these, but maybe we were out of good prefixes. Physics ran out of good things to call things a long time ago. So, base to kilo is 1,000 times bigger. Kilo to mega is 1,000 times bigger. That means base to mega is 1,000,000 times bigger. So 24 megajoules is how many joules?
24 million?
24 million. Very good. So that's a lot. Of course, a kilogram of coal is a lot. It'd probably take up a brick about this big. So it'll burn a while. It'll get pretty hot. Now let's say that this coal is burning in some sort of a power plant or maybe in a steam train. And usually the reason we would burn coal to get energy is you burn the coal, you put like a water tank above it, The fire literally just heats up water, makes it evaporate, and the steam runs a steam engine. Turns out a lot of our power plants are really just glorified steam engines. Whether you're burning coal, oil, or nuclear processes, you're just running a steam turbine. So, this 1 kilogram of coal will release this much energy when burned. The problem with burning anything is the thermal energy is not all going to go exactly where you want it to. If I had a fire right here on this table, a lot of the heat would rise, but some of the heat will enter the thing the fire is sitting on. Some of the heat's going to enter the air and drift away from the tank. Burning is really inefficient because the heat just goes everywhere. So if you wanted it to end up in, your water boiler, it's not all going to make it there. This particular process, only 10 of these megajoules actually makes it into the process we want it to. So if we put 24 megs in, we get 10 megs out. So my first question is, how much energy became internal energy that is not doing any work?
So it's not doing any work?
Right. So this amount is the work that the machine does.
I was going to say
The machine does this much work, but we powered it with this much.
So 14.
14 megajoules, very good. To give you some formulas and numbers to put in your notes, remember from last time, delta U equals Q minus W. Delta U tells us the change in the internal energy of a system. We are adding 24 megajoules, and it does a 10 megajoules worth of work. Both units are megajoules, which means that we're just going to get megajoules out for our answer, which is fine for right now. So that means 14 of those 24 megajoules are now doing nothing more than just making the machine hot. This energy is not doing work. This energy is not going to power your car or make the train move. This just pointlessly makes things warm. It's now in a state where we cannot use it. In fact, in this state, it's more of an hindrance than anything else. The next question, what is the efficiency of this system? So, we have a formula. We're solving for efficiency, so we want our output was 10 megs, our input was 24 megs. So, if I remember correctly, that should give, just dividing 10 by 24, should give you 0.4167, which is 41.67% effective. Your efficiency for any real machine that actually exists will always be some decimal value between 0 and 1. If for some reason your efficiency is over 1, that means the machine does more work than you gave energy to, which defies physics as we understand it. You would win every Nobel Prize ever. Because that means you can produce energy and you violated physics as we understand it. So realistically, this value will always be a fraction, a percentage between 0 and 1. And this, if this number seems wasteful, like if 42% of this energy is being used, that means 58% is just being wasted. And if that sounds wasteful, this is more efficient than most real machines. Purely in terms of food intake versus mechanical energy output, the human body is only about 20% efficient. 20% of the energy you consume, last I heard, I'm not a biologist, so take this with a whole packet of salt. In terms of just of food intake versus mechanical output, the human body only actually can do 20% of the work that you eat in terms of energy. Some of that is by design. We are warm-blooded organisms, which means our bodies intentionally take some of that energy just to make heat, just to regulate our temperatures, which on the plus side means we can actually be active during the winter. On the downside, it makes summer really unfun. But human body is like 20% efficient. I think a real coal engine would probably be even less efficient than this. So this is a really good coal engine, actually. Everything has some percentage like this. Theoretically, if you built a machine that was 100% efficient, if the output equaled the input, then entropy would not increase in that interaction because you didn't lose any energy to the thermal state. That would also be some perpetual motion, and you would also win a Nobel Prize for that. Because if no energy is lost over time, the machine would never stop or slow down, and again, would win many prizes if you do this, if you could ever create a 100% efficient machine. Good luck. I haven't figured it out yet. So, efficiency always tells us how much energy is actually utilized. So if that much is actually used, then we lost about 58%, which is, this number is 58% of the total energy input. So you can use this a couple of different ways to figure out the energy that was used successfully, the energy that was lost, etc. Any questions about thermal efficiency? Okay. We're about to switch gears. There's one more concept for all of the thermal energy chapters. And since we're switching gears, if anyone needs a minute to collect their thoughts, get water, etc., now's a good time. I certainly need a sip. I've been talking way too much today. Okay. Final stretch here. I don't expect this to take the rest of the period, so we'll have plenty of time for questions afterwards. So, the last principle involving thermal energy that we're going to cover in chapter 8. We've already talked about conduction specifically. conduction is specifically the act of thermal energy transferring through direct contact between two objects. Right now, when I touch the board, I feel the sensation of cold. That means thermal energy is leaving my hand and entering the board through the direct physical contact between us, and this will keep happening until we are both at the same temperature. Most of this is not new information. But what we're going to start looking at here is the rate at which thermal energy flows between two objects. The human body does not have a built-in thermostat. When you touch something, there's no part of your nervous system that says, ah, yes, this is exactly 72 degrees Fahrenheit. You don't detect temperature that accurately. All you can detect is whether or not thermal energy is leaving you or entering you. And when you feel, the hotter something feels, that doesn't necessarily mean the object you're touching is at a higher temperature. It just means that thermal energy is entering you more quickly. The hotter something feels upon touching it, it means thermal energy is entering your body very quickly. It doesn't necessarily mean that one object is a higher temperature than the other. All it means is more thermal energy is coming in per second. Similarly, the colder something feels, the more thermal energy leaves you per second, regardless of the actual temperature of whatever you're touching. As a sort of demonstration of this, I'd like us to run a quick sort of demonstration, and if at least one student could do this physically so that it's not just me saying to you what happens, I'd appreciate that. Let's say that you wake up in the morning, and when you wake up, your dorm, your room, your apartment, your house, overnight everything should have been sitting at the same temperature, correct? Your thermostat is set at night, the air conditioning is going, so everything should be at the same temperature. No one's been moving around or warming anything up. All the air, every physical object, they've all been touching, they're all in the same system, they should be in thermal contact and have reached thermal equilibrium. And I guarantee that of this room too. Until you guys came in here, this room had been empty for a while, no one had been touching anything or moving around, so everything except the humans in here should be about the same temperature. Now, I'd like at least one student, if you don't mind, to come up and touch two specific objects that are in this room and should be at the same temperature. The first object is going to be the lid of this styrofoam cup. The second object is going to be the metal top of this scale. Anyone willing to engage in this activity? All right. Thank you very much. So, just if you could, just put one hand on each object, or even just one finger if you want. Tell me what you feel.
We were about the same temperature. Well, the metal was cooler at first.
Okay. So, you felt colder touching the metal. Does everyone agree that that sounds like what you expect to feel here? And you can try this yourself, even at your own table, if you have a metal object nearby. Actually, even if you wanted to, you could probably even compare the surface of the desk to, say, the paper you're writing on. Thank you. You expect to touch things that feel like they're at different temperatures during the day, but I guarantee you most of the inanimate objects in this room are at the same temperature. And yet, the metal stuff feels colder than wooden materials or paper or styrofoam materials. Even though they should be at the same temperature, the metal ones still feel colder. Why do you think that is? Specific heat does factor into it. If either object is a fraction of a degree less than yours, thermal energy will exit your body. And Metals do have lower specific heats, so they will probably eat up more of your thermal energy more quickly. They need more thermal energy than those in water. Take a sip every time I get tongue-tied. Now, specific heat does play into it, but there's a related principles similar to specific heat in that the constants tend to line up, but what's happening in this particular case is different materials conduct heat through them at different rates. Certain materials naturally either allow heat to travel through them very quickly or they don't. Perfect example is actually styrofoam. Does thermal energy pass through styrofoam very quickly? No. Styrofoam is by design an insulator. If I put something hot in this cup, the outside of it will not feel hot because the cup is designed to keep the thermal energy trapped inside. Thermal energy does not transfer through the wall of the cup very quickly because of what it is made of. Meanwhile, if you stick a metal rod into boiling water and you just touch part of the rod that's not in the water, it's still going to feel hot very quickly. If this was a metal cup, the heat would transfer very fast. That's a better example. If this cup was made of metal and I put boiling water in it, you'd feel it, right? Very quickly. Different materials conduct heat at different rates. And so we're going to get to the formula in a second. You can go ahead and keep copying now. This chart here, I already gave you a specific heat chart. We're going to keep that chart. This is new information. You will also have access to this chart. But this tells us the thermal conductivity of different materials. And the higher these numbers are, the faster thermal energy will transfer through the listed material. This is thermal conductivity, which tells us energy that transfers through an object per second. The higher this number is, the more energy will transfer through an object per second. So if we look at these values, they're sorted into three separate categories. We have metals at room temperature, and these are all pretty big numbers because metals conduct heat very well. They also conduct electricity very well. Usually if something conducts electricity, it also will conduct heat. Usually. So these numbers are very high. Meanwhile, the gases and the nonmetals have very, very low thermal conductivity because heat does not transfer through these very easily. Styrofoam is not actually up here, but rubber is another thermal insulator. Usually if you want something to not burn you, it could be styrofoam lined, it could be rubber lined. You've also got water, which is also a good insulator. And then there's air, which has one of the lowest specific heats on this, thermal conductivities on this table. Air is a very good thermal insulator. Thermal energy does not transfer through air very easily. So every different material just has a naturally different rate thermal energy will transfer in or out of it. And so when you touch something and it feels really hot, yes, it could be at a higher temperature, but it might also be made of something that very easily allows thermal energy to exit it and enter your hand very quickly. If this styrofoam was at a very high temperature, you likely wouldn't feel it because the thermal energy would not leak into your hand very fast. It would still happen, just very slowly. So, how we utilize this research, people had to study each material and find what these values were. How we utilize this is by looking at the rate at which thermal energy flows through an object. And since this is energy flowing over time, this is technically thermal power. Because energy over time is power. So it's this right here is the same formula we used in the last section, the last core of the class. Energy over time is power. As energy transfers, there's an amount of thermal power that flows from one object to another. And the rate at which that thermal power flows depends on, actually, ignore this part, because this part is less informative than this part. We've taken this and we've expanded it down here. So this is just the rate, the amount of energy that flows over time. This formula, though, factors in every single variable about the object that the thermal energy is transferring through. Physics uses formulas to describe the universe, so we are going to describe every piece of this so it's more obvious what each element means. So this formula here talks about the rate at which thermal energy flows through an object. Power is that rate, so that's still energy over time. It's still power, it's still measured in watts. The K are these. Lowercase k refers to thermal conductivity. Oh, hello, notes from yesterday's lab. I forgot you were there. So K is the thermal conductivity, which is everything in this table. Every material has a different one. You don't need to memorize any of them, like specific heats. A is the area through which the thermal energy flows. So, for example, let's say we're looking at the wall of your house. So let's say this is by itself a single wall of your domicile. Now, this particular wall, the point of a building is usually to keep the inside in and the outside out. So let's just assume, let's do winter examples since we're getting into colder months. If this is the inside, you want the inside at this temperature. And the outside is some amount colder. What direction is the thermal energy going to flow through this wall? It's going to go out. It's going to go from hot to cold. So thermal energy is going to try to go through the wall outside. This is true of all buildings. Now, what the wall is made of affects how fast that energy is going to leak out. Most buildings are made out of some combination of wood, metal, and they don't list drywall and fiberglass up here. But various materials, usually designed to help insulate your home. But what it's made of is not the only factor. Additional factors that affect the rate at which thermal energy is going to transfer through include the area of the surface in question. So the area literally being the surface area, the length times the width. All right, it's height in this case. The more area there is, the more wall there is for thermal energy to be passing through. The bigger a door is, the more people can fit through it. The bigger a wall is, the more thermal energy can flow through it at any given moment. There's more wall on this side exposed to the colder air. So the bigger the wall is, the more thermal energy can transfer through it every single second. So distance A is the area, it's the flat surface area of whatever side you're looking at. This term here, temperature hot minus temperature cold, this is the difference in temperatures between both sides. So the temperature difference up here is going to be 5 degrees. In this particular formula, what this tells us is that heat transfers faster if the difference between both sides is greater. If one side is a lot hotter than the other, thermal energy will transfer through more quickly. Energy likes to go from high concentration to low concentration. The higher the concentration is, the faster the heat's going to try to get out of there. So heat will transfer more quickly if there's a greater difference in temperature across both sides. If the temperature difference is lower, this would be a smaller term here, and that would decrease the rate at which thermal energy flows. The last term, whoops, I shouldn't have called that L. I'm sorry. That's width, that's height. Sorry, I shouldn't have used L, because L is reserved for something else. This is the thickness of the object, or the length that the thermal energy has to travel through. The thicker an object, the longer it takes thermal energy to get from one end to the other. That's why that term is on the bottom. If L gets bigger, it's going to make P smaller. Meanwhile, if the object is very thin, thermal energy will transfer through it very quickly. So a smaller number down here would make P larger. Usually if you are shopping for a cup or a thermos that you want to stay cold all day, if the lining is thicker and filled with a good insulating material, then thermal energy will transfer through it more slowly. Meanwhile, a paper cup that's maybe a centimeter of paper thick, heat's going to transfer through that a lot more quickly because it's very thin. There's less distance for the heat to travel. So that's why these are usually a lot thicker than paper cups. Similarly, this is pretty thick styrofoam, actually. So the factors that affect the rate at which thermal energy will transfer through an object are what it's made of, its surface area, the temperature difference between both sides, and how thick the lining is. To get my undergraduate degree, I had to study refrigerators for a project here at PC. And a lot of my math was actually this formula, because the energy efficiency of a refrigerator depends on how much thermal energy passes through its walls. So I guess this was kind of my capstone work. Now, to show this in action, I will rewrite that formula on the other side of the board because we're about to use it. The formula was power equals K times A times temperature difference between both sides divided by L. So, the question is, what is the thermal power rating, what is the rate at which energy will flow through a pot with a copper bottom? So we do know the material in question here is copper. So in a second we need to look up the thermal conductivity of copper. The chemical symbol for copper is Cu. That's what I've written up here. So in a second we're going to look up on the table thermal conductivity of copper. We are told that the heat is transferring from a hot reservoir of 300 Celsius. That is I'm going to assume that's the temperature of the burner under the pot. Heat is going to flow from the hot to a cold the cold side is filled with ice cold water, and ice, we're just going to take that as 0 degrees Celsius. So the temperature difference between the two sides is going to be 300 minus 0, which is 300. You can use Celsius here because the difference between Celsius here is the same as the difference between Kelvin here. You're also told, and we're going to assume that this particular pot is circular. Which means that its base is 2 millimeters thick, which is not a lot, and that its bottom has a diameter of 12 centimeters. So, look at our formula. We want P, we want the power that transfers through. We need to find the K value for copper. So we're going to go back one slide and look at the table. So thermal conductivity of copper in joules per second per meter per degree Celsius is 397, yes, 397. The unit's not super important here. Those units are only listed so that everything cancels correctly. So that is the thermal conductivity of copper. So we know K. We know the temperature difference. We know how thick the bottom of the pan is. We do need to take a second to find its area though. We know its diameter, but if it's a round pot, then that diameter tells us the bottom is circular. So we need to find the area of a circle whose diameter is 12 centimeters. And, no, I always misremember this. One of the reasons I give you guys formula sheets is because I don't even remember the formulas half the time. Because I have my books and notes with me all the time. So I don't see much point for depriving you of them. Alright, the area of a circle, yes, that's what it was. And if this type of if you were asked a question on like the homework, would you need this formula? This is completely fair game. Any formula that you need to look up is fine. Homework, the internet is yours. If you need to also email me. So, the area at the bottom of the pot is going to be pi r squared. So pi times radius is half of diameter. So first, 12 centimeters is going to be 0.12 meters. Half of that is 0.06 meters. Square that, and that'll tell us area of the bottom of the pot. About this number. Okay. So that's our area. We now know every variable. We can just start plugging things in. Power equals 97 times our area times our temperature difference divided by the thickness. What's 2 millimeters in meters?
0.002?
Yep. It's 1,000 times smaller, so you move the decimal place over 3 times. And now we are good to simply find our power. Does anyone's math disagree with 673,494.63 watts? And that is a lot of watts. That's higher than the wattage of most appliances, just in terms of energy per second. And if you remember, 1 watt is 1 joule per second. For every second, that many joules move through the bottom of this pot, which is a lot. 300 Celsius is also a really high temperature to begin with, and copper conducts thermal energy pretty quickly. Someone have a question? Sorry.
No, well, we usually need to convert that to Kelvin, because I remember you saying that the ratio for 300 to 0 is like the same as Kelvin. But will we usually need to convert that for like a problem like this?
If the problem is basically delta temperature, if the problem is change in temperature, like it is here, final minus initial, hot minus cold, then it'll work either way, since the conversion between Kelvin and Celsius is just adding a number. Then the difference here is 300. The difference would be 300 in Kelvin too. So change in temperature, Kelvin or Celsius works. But if the formula asks you for the temperature that isn't changing, it has to be Kelvin. Yes?
Will every problem with convection, every answer, will it be watts?
The standard unit is watts, yes. I don't think any of the homework problems would ask you horsepower. That's the only other unit of power we've talked about. So it should be watts. Now, for one, this is a lot of energy, but you would want energy to quickly transfer into your water to warm it up if you were trying to melt it. Warm up this particular water. Where this is also important is for architects and people making appliances like refrigerators, because if you are building a house, you want to take into account how fast thermal energy transfers from one out of the building or into the building during summer, because if that the bigger that number is, the faster the temperature changes. And so if you were to plug in the numbers here for this wall, temperature difference, its area, its length, what it's made of, and you had a high thermal power through this wall, you'd have a really uncomfortable house, because it would be hot in the summer and cold in the winter. And that's the end of chapter 8. So that's every formula that you need to do your chapter 8 assignments. And I will soon be putting out an official chapters 5 through 8 formula sheet with all those formulas on it, and so that you can use it on the upcoming test. It's not yet. It's soon, but not yet. And also practice question with formula sheet for it. Now, we're done with chapter 8 material. So, first, does anyone have any questions about anything at all about chapter 8, assignments, test upcoming, anything at all? Okay. Now, that, chapter 8 is done. If you don't have any questions, I'm fine from break here. You guys get to your weekend a little bit sooner. I know it's Thursday, but still. Pardon me. That said, be working on your assignments and send me questions as soon as you have them. I highly encourage you to be working on your homework now, because A, everyone emailing me at once Tuesday night doesn't really help anybody. B, the sooner you work on it, the sooner you can start working on test prep. Information for that will be made available to you soon in terms of like form the sheet to practice questions. Right now, just focus mainly on chapter 8 homework and quiz, and some questions when you have them. And if I don't see you anytime soon, have a wonderful day. Also, vote Tuesday if you are from this country. That's important.
Isn't there left?
Sorry?
Isn't there left?
There is. If you are